Okay, if we look at the first one, okay, what we're changing, right, is we're moving this proton here. And so therefore we can compare these two groups, right? If we compare those two groups, we have an oxygen, sp3 oxygen, right? But an oxygen is more stable with the negative than the carbon because it's more electronegative. This is an sp, so we do need to consider that. But is there a switch between oxygen and carbon when you change the hybridization? And that's a no, that's nitrogen, right? A nitrogen sp3 is less stable than a carbon sp, but not the oxygen. So that means this is the most stable out of those two, right? So that means that I would think this is going forward. If you know the relative ranges of the pKa's, you know that this has a higher pKa, right? This has a pKa around 25. This has a pKa, you know, of about 16, right? So again, we're going to go towards the higher pKa's, right? So we want to go from high acidity to low acidity, and that's the forward direction. And the next one, right, again, we're going to compare this to this. If we look here, we have resonance, right? They're both oxygen negative. So if we look at atom, resonance, inductive, and orbital, we have both oxygen negatives, right? So oxygen negative, oxygen negative. They both have resonance, right? But then this one has inductive. Right? So we have an inductive pull towards the fluorines, right? So that's going to make this more stable, right? And then more stable, and this is less stable. So we're not going to the less stable, right? We want to go to the more stable, which means that the equilibrium on this one would be going backwards, right? So the way you answer these is to look at your conjugate bases or your acids. Now, we can't really use pKa here unless we looked them up, right? It's the pKa's are going to be different, but it's not like we would have known the ranges, right? So they're both carboxylic acids. They'll both be somewhere between pKa of 2 to pKa 5. Right? So, all right, next, let's look at nomenclatures of alkanes. Okay, and let's name a few. So let's take a minute or so. If we look at the first one, right, we have pentane here. So we have 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's always important to double count, take your time with these, right? These are the easy problems, so you want to make sure you get them right. And so this is going to be 2 methyl pentane. So if we circle our pentane, right, then we have the methyl attached to that. Okay. On the next one, our longest chain here is actually the ring, right? right? So we have our 6-membered ring, that's going to be cyclohexane. Then I have a methyl and an ethyl. So ethyl, methyl. And, you know, if we number that, we could have 1, 2, 3, or we could have 1, 2, 3. So either way, they're going to be 1, 2, 3. So in this case, we're going to use the alphabetic, right? So the E comes before the M. So therefore, this is going to be 1 ethyl, right? 3 methyl, methyl, cyclohexane. Okay, questions about that one? Except the fact that this. Thanks for putting up with my bad handwriting. Okay. Questions about that? All right. So again, alphabetic here, we have a similar thing. We have the alphabetic, we have the bromo and the chloro. So the B comes before the C. So therefore, this is going to be 2 bromo, 4 chloro pentane. And for some reason, I'm stuck on pentanes today. So pentane. This one, 1, 2. If we look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? We can count it this way: 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Right. So 9 is going to be the longest chain, which means I have 2 ethyls on there. And so this is going to be nonane. And if we look at our, we got a 4, 5. If we went the other way, it would be 5, 6. So this is going to be 4, 5. And then we use the prefix di ethyl, right? And all one word, no space. Okay. So hopefully by now nomenclature is pretty straightforward. Again, you know, you'll see some of these, no reason to have all hard questions on the exam. Next area probably might have forgot about is Newman projections. To give you a hint, right, that's these projections. Okay, so I'm going to draw a structure and I want you to replicate that in a Newman projection. Okay, and then I want to look down, right? I'm going to put my eyeball here. You won't see this on the test, right? You're not going to see the little eyeball, but this is a C2 to C3 projection. Okay. All right. So let's do that one. Okay. So when you do a Newman projection, you know, just go ahead and, you know, and again, have some scrap paper. Go ahead and draw your structure. So the 3 lines that are going to the middle, that's going to be the first carbon. And then the lines on the back, right, that only stop, that's going to be on the back carbon. And we're always looking down 2 carbons. And again, the eyeball won't be on the test, but the way they say this is show the Newman projection down the C2, C3. And this is the C2, C3. It turns out that if I had gone here to here, it would have been the same thing, right? That would be different than if I had said C3 to C2, right? C3 to C2 would have had the ethyl in front and the methyl in back. Okay. So when I put those in, right, then that means if I look down the structure, what's going up? And I have the methyl, right? So there's the methyl. I have a hydrogen coming to the front and a hydrogen going to the back. If I look here, what's going down? What's going down is my ethyl, so I write that in, right? And I have my hydrogen and my hydrogen. Questions about that? So let's try one more of these. So we got our little eyeball. This is going to be down the C3C2 bond. Okay, and let's take a little time to draw that one. Okay, if we look at this one, we have our structures here, right? So here we're going to put the ethyl up at top, right? I haven't shown the hydrogens, but they're going to be forward and backwards. And then in the back here, notice I didn't put it as staggered. I put it as eclipsed, right? And so this is the eclipse form. So that's the other part of this to understand, right? This is an eclipsed, right? This is a staggered form, right? So if we look at between these two, right, this is going to be the most stable. Okay, so we get most stable and then the eclipsed. There's something else I want to say about this. Okay, if you have to find different species, you have gauche, right, which would have the two groups closer together, but not fully anti. So this is actually not only staggered, this is anti, right? I could have also shown this structure. Right, and this is gauche or gauche. Questions about that one? Okay, which one is eclipsed? Okay, this one, if you look at it, the way that it's shown here, right? If we think about three dimensionals, that means these hydrogens are coming in and out. So when I'm looking down this, right, looking down this bond, right, this bond here is going to be in front of that bond here. That means this bond is eclipsing that bond, right? I can't really show that, so I show it tilted as if I moved it a little bit. So therefore, this ethyl is eclipsing that methyl, right? Up here, when we look at it, we get anti because the two groups are on opposite sides to each other. So they're staggered, right? Eclipsed is whenever they're lined up. And then, of course, this is gauche, but it's also a staggered, right? So there are two forms of staggered. For eclipse, there's not formal terminology. Usually what's called a high energy eclipse and a lower energy eclipse. This, because the two biggest groups are attached, would be your highest energy eclipse. So if we look at the rotation energy wise of these, you would go from, eclipsed up to staggered, anti, right? Anti here to eclipsed to gauche to high energy, to gauche, to eclipsed, to anti. So as you rotate around that bond, right, you're getting different energies. And of course, the lowest energy is going to be the anti, which is the one I showed first. Does that help with these? All right. Okay, let's go ahead and look at cycloalkane conformation. So these are conformations, right? This is, in all of these, I haven't changed my molecule. All I'm doing is rotating around this bond right here, right? So I'm getting from one to the other without rotating. These are not conformations, right? I'm not changing the connectivity, I'm changing where they are in space. So it's a conformation. So the other type of conformation we need to look at is chair conformations, right? With cyclohexanes. So if we think about cyclohexanes, they want to form the most stable. So take some time and draw me the chair conformation, the lowest energy, for this compound, right? And if you don't remember, that's what the chair conformation looks like. Okay, so let's take a look. Okay, so we start by just drawing a chair, right? Like this. And then I'm going to put, you know, the methyl kind of the way it's shown. Right. So if we look at that, now what I have is, here's a chair conformation with my two methyls. This methyl is obvious going up, right? This methyl is obviously going up, and this methyl is obviously going down. But then I need to think about the fact that this was asking for the lowest energy. What position are my methyls in? Well, this is an axial position. So if we think about, you know, that being my axis, axial positions will be lined up with that axis, right? Versus, you know, these positions, and let's change our color. I deleted my line. Okay, if we look at, you know, this position and that position, these are equatorial. So if we're thinking about space, right, if you are on the equator versus the Arctic Circle, right, where would you be closer together if somebody else was standing? Well, it's easy to say, unless you were standing next to each other. You know, equator is going to be much further apart than the Arctic Circle. So, you know, Africa is further away from our Sahara Desert is further away from, let's say, the Panama Canal than you know, Iceland is from Siberia. So therefore, equatorial is actually going to be the more stable. So what I want is the largest groups, and think largest group spatially, right? Largest group in the equatorial. So therefore, this is not the correct structure. So if I had drawn this on my note paper, this, I should know that that's not the most stable. So what I want to do is flip this, right? And this is called a chair flip. And what happens now is the CH3 is here and the CH3 is here. It's still the same structure, right? I haven't changed it. I've just changed the way I'm looking at it, and I've flipped the two. Now the hydrogens are in the axial and the methyls are equatorial. Questions about this one? Let's try a couple more of these. So draw the most stable chair conformation. Okay, if we look at these here, okay, this first one, the best way to really do this is just go ahead and draw one, right? And so, you know, let's draw our OH there, right? And then we can draw, so we need to think about the two positions. So if we want it opposite, right? If the hydrogens are here, our ether group, our ethoxide group is going to be here. Ethoxy group, actually. So our ethoxy group is going to be here. And if we look at this drawing, right, I've again put this axial and that axial. So what I want to do is flip this. And again, the way you flip it is you bring the group this up, down, right? So you don't change, you don't switch this, you flip the whole thing, right? So I'm flipping it. And I'm not flipping it like this. I'm flipping it by going down and up, right? They're hard to find now, but they used to have these lounge chairs that had these like ratcheting sides, and you could have one end up or the other, and really think about that. Like, you know, I did it to my sisters and me. You know, there was a button you could push, and it would make your head fall, and you could pull their legs up, and their legs would be in the air, and their heads would be down at the ground. But if you draw it incorrectly, all you have to do is flip it, right? And so when we flip this, then again we have the two positions here. We've got our two positions here, and now the hydrogen goes into the axial, right? And I have my alcohol in the equatorial, right? And I have my ethoxy in the equatorial, okay? If we look at the other one here, we have two at the same side. So we can just, let's say, put the OH going up, put the butyl group in the going out, right? And in this case, now we have an axial and an equatorial. And if we think about it size-wise, which one is really bigger? Well, this is going to take up more size, so this is the correct one, right? I put my largest group in the equatorial position. Questions about chair flips? Okay. Again, do a little practice, get comfortable with. Again, you probably haven't seen them for a while. Okay. So let's move into the next chapter, stereochemistry.
Can you go up for 1 second?
Yeah, no problem.
Thank you.
Okay, so for stereochemistry, one of the things we need to think about first is identifying chiral centers. And so let's identify some chiral centers. Okay, so mark all of the chiral centers with an asterisk. Okay. Okay. All right, so if we look at the first one, we have a chiral center right here. And what makes a chiral center? We just need 4 different things attached. Right, so first thing, they can't be sp2, right? They need to be sp3 for chiral centers. And we need 4 different things attached. And here, the thing that's not shown is the hydrogen, right? So when we look at that, those are different. Here we have a chiral center, right? Over here, now we get a little bit more difficult, right? We have, it looks like we have 4 things here because we have a hydrogen, this group. But if we look at this side and this side, we end up at the same place, right? So there's symmetry. There's a plane of symmetry, which means if I put an imaginary plane right there, I can divide that molecule down the middle. And I would rotate this one to be in the plane to do that division. And so therefore, this position is not a chiral center, but this one is. Okay, so that one only has 1 chiral center. Here, we have 2 chiral centers. Here we have 1 chiral center, but what about the double bond? Can that be a chiral center? No, but it can be a stereogenic center. Right, so that could either be the trans that it's shown here, or it could have been the cis. Right, so it's not a chiral center, but it does have stereogenic nature to it. It's going to have 2 possible conformations. It's going to have a cis and a trans. Okay, so if we look at those are our chiral centers. Right? Should be able to name chiral centers, right? So let's do some RNS naming. So let's go back to this one. Let's start with something easy. Okay, and let's name the R and S for these. You don't have to name the whole thing, but if you have time and want to do that, you can. Okay, if we look here, so what we're going to do is using the atomic number, we're going to set up our priorities. You should always go ahead and show what's not there so you don't forget about it. So here, I'm going to break it out first just so you can see the long scale. So what we have is a bromine. That's going to be 1, right? Because it's got a highest atomic number. Hydrogen is going to be 4. Then we have our 2 carbons, right? If we look at this carbon here, so let's call this, the carbon A and carbon B. So if we look at A, what is A attached to? Well, A is attached to a carbon and 2 hydrogens. So therefore I put carbon and 2 hydrogens, which means that it's going to have another addition, right? You're going to have another carbon. If we look at B, the carbon is just attached to 3 hydrogens. So you don't look at what it's coming from, right? You already know that. You look at where it's going out. So you're looking forward. So here we can already see that although we can go further with carbon A, we don't have to. The difference between the carbon and hydrogen here says that this is going to be my 2. Oops. This is going to be my 2, and this is going to be my 3. So if we come back up here and put that in, so here's 1, 2, 3, and then 4, I can see that I want to draw an arrow from 1 to 2 to 3. That's going in the clockwise direction, and clockwise direction is going to be R. We'll do the same thing with the chlorine up here, and I'll do it a little faster. So we get 1, 2, because this is attached to a carbon, 3, because this is only attached to 3 hydrogens, and then 4, right? We do our 1 to 2 to 3. Now we're going counterclockwise. That is S. And I should have said, right, you need to check your lowest priority. And my lowest priority is back, right? So therefore S is correct. Over here for the R, the lowest priority is back. So my R is correct. If we look at this one again, oxygen is going to be higher than the 2 carbons. Hydrogen is going to be the lowest priority. And then we have these 2 carbons. So if we look at our carbons, again, let's refer to them as A and B. Carbon A, right, is attached to a carbon, but it's double bonded. So we'll add another carbon and a hydrogen. That's the way you look at double and triple bonds. If we look at C, we only see it attached to another carbon and then 2 hydrogens, right? So therefore, A gets 2, and B gets 3, lowest priority, highest to lower priority, we're going the R direction, lowest priority is back, so we stay at R. Questions about R and S nomenclature? Okay, let's look at 2 more. And 2 examples of situations where we may have something a little different. So let's try these two. Let's take a look. So again, looking at our numbers here, bromine is going to be 1. And then our lowest priority hydrogen is up, right? That's 4. And then we have our 2 carbons. The first iteration of the 2 carbons is the same, right? They're the same. But then when we get to this center, right now they're different. And that gets a higher priority, right? So this will be 2, and this will be 3. So if we draw our arrow from 1 to 2 to 3, right, in that direction, that gives us S. But where is my lowest priority? My lowest priority is coming at me, right? And I'm always supposed to have the lowest priority away from me. So that means this is not S, it's R. I can reverse it. Now, why can I do that? If we think about this, if I could be on the opposite side of the paper, or in this case, the iPad, right? Would the lowest priority be away from us? Yes. And if I was looking at a clock from the other side, so imagine I have a glass clock and I was looking at it from behind, what would happen to the hands? Well, the hands would look like they were going counterclockwise, right? So if your lowest priority is pointing at you, right, then what you can do is reverse it, right? So if you find S, check your lowest priority. If your priority is forward, then you're on the wrong side of the paper. Okay, if your lowest priority is back, then you're on the right side of the paper, right? You're looking at the molecule the right way. The next one, we have an example of the lowest priority in the plane. So if we look here, we have 1, 2, and 3, but here the lowest priority, 4, right, is in the plane. It's not going forward or back. If it was going forward or back, we'd be in good shape. But it's in the plane, which means now I have to redraw. I can't name this one correctly without redrawing it, but it's very important how you redraw this. And the way to think about this is spinning an umbrella. What I want to do is I want to spin these groups to either get the hydrogen forward or back, or the lowest priority forward or back. So, you know, you can check either edge, but I'm going to show an arrow going here, here, and then here, right? What I'm going to do is spin around that group, which then I'm going to redraw my base structure without anything attached to it. And then I'm going to follow my instructions above, right? I'm going to take my hydrogen moved back. So then I'm going to put them in pink so you'll understand the connection. So hydrogen goes back, the methyl comes forward, and then the bromine goes to the top, right? So all I've done is use those arrows to redraw this correctly. It's very important because you can redraw this incorrectly. And I can end up with 1, 2, 3, right, and 4. Now when I draw my arrows from 1 to 2 to 3, right, that's going in the R direction. My lowest priority is back, so I can stay with R, okay? Right. Now I'm going to skip ahead a couple of chapters and we'll look at E and Z. Since it uses the same nomenclature, so let's name let's name these two as E and Z. All right, so let's take a look. So the thing we want to do here is we want to compare the priorities on one side. So I'm going to look at just the left side and just the right side. So if we look here, right, this gets 1 and that gets 2 because one of them is attached to more carbons. On the other side, we have our hydrogen, right? And of course that's 2 and this is 1, right? So that's the first thing, is to set those priorities. Then I want to compare along that double bond, so not bisected, but look parallel to it. And now we look at where our 1s and our 2s are, and we see that the 1s are on opposite sides, right? So they're on opposite, right? So that makes it E for opposite. All right, so E is going to be opposite, right? And so this would be an E nomenclature, right? Now, could I use cis and trans on this one? I can't use in cis and trans because it's 3 substituents. So cis and trans doesn't work on this one. I have to use E. Well, the next one, again, we'll first compare our groups on each side, right? Here I get 2 and 1, right? So now when we look at these, right, I see that my 1s are on the same side, right? So this is going to be Z. Now in this case, could I use cis or trans? Yes, it's only di substituted. So this could also have been referred to as cis, right, on the same side. Okay, so E and Z. Questions about E and Z nomenclature? Again, it follows the same priority rules that we use with R and S.
Professor, was there
Yes.
something about like if they have both methyls on the same side or something like that, they don't, am I thinking of something else?
Are you thinking something like this?
Okay, maybe.
In this case, it doesn't have a nomenclature because it doesn't have a stereo nomenclature because it has symmetry. You might have been thinking, you know, the early cases of cis would be something like this, right? Or this, right? So here you can just look at what the groups are on the same side, but as far as E and Z, you should follow the RNS nomenclature protocols. That's the best way to get the right answer. For cis and trans, sometimes they'll define it as having the same group on the same side or having the same group on the opposite sides.
Okay, thank you.
Mm-hmm. All right. Want to talk a little bit about optical activity. And this one is less of a problem than just reintroducing this. One of the things to remember about optical activity is that if I have a rotation of, let's say, plus 25 for this molecule, then this molecule, which is its enantiomer, right, will have a negative 25. Right, and an enantiomer is a mirror image. So to be optically active, something has to be chiral, right? So stereogenic centers don't work, it has to be chiral. And then if I know the optical rotation for one enantiomer, I can determine the optical rotation of the pure other enantiomer. And if I had a 50-50 mixture of these two, right, I know that I have a racemic mixture. Right, and that's actually where the term comes from, is racemic was that things that should be chiral were coming out with 0 degrees optical activity. So you could take a material that was optically active, go through, let's say, an SN1 reaction that has a racemic product, and then all of a sudden your optical activity would go to 0. Right, so there's ways to calculate this. Again, if you get into advanced chemistry, but really what you need to understand is that optically active compounds have a very specific optical rotation, and that optical rotation is important. If you ever see medications with a plus or a minus and a number behind them, those compounds are optically active, and they should only be sold as an optically pure compound. There have been cases where pharmaceuticals were sold as racemic mixtures, and one of the isomers was helpful and the other one caused, in the worst case, birth defects. Okay. All right, let's move on into looking at enantiomers and diastereomers. So label these for me. Oh, we're almost out of time, but let's do one real quick. So let me know if these pairs are enantiomers or are they diastereomers? Okay. In the first case, these are going to be diastereomers, right? They're non-superimposable, non-mirror images, right? They're not mirror images, so therefore these are going to be diastereomers. If we look here, right, these are going to be enantiomers, right? They're going to be mirror images. If I look at naming these, right? So if we go 1, 2, 3, right? This is going in the R direction. If we look here, 1, 2, 3, this is going in the S direction. Over here, we have 1, 2, 3, that's going in the R direction. And here, 1, 2, 3, that's going in the X direction, but the lowest priority is forward. So this is actually R. So you can tell this diastereomers whenever you go from RS to RR. So if you only change one of those two, that's going to be a diastereomer. So if you go from RR to RS or SR, or if you go from SS to SR or RS, right? Those are all going to be diastereomers. Here we only have one stereocenter. And so what we just need to confirm is that this stereocenter is changing, right? So there's going to be enantiomers. So if I went from RS to SR, that's an enantiomer, right? So if I change both groups, it's an enantiomer. If I change one of the two groups, then it's going to be a diastereomer. Okay. All right. That's